Hello. And welcome back to the Umbrella Academy.
In this lecture, we will discuss conformations of ethane and propane. Consider the sawhorse projection of the ethane molecule. In drawing conformations, we often use Newman projections. For a detailed lecture on Newman projections and interconversions of different projections, click here. To convert this sawhorse projection into Newman projection, look through this carbon-carbon bond. The front carbon is denoted by green dot and back carbon by red circle. Front carbon has one hydrogen pointing down, one on right pointing up and one on left side also pointing up. The angle between these hydrogens is 120 degrees. On the back carbon, hydrogen is pointing up. Another one on right pointing down and one on left also pointing down. Let us keep the back carbon stationary and rotate the front carbon by 180 degrees. The back carbon and its hydrogens remain unchanged and are written as such. After rotation, the bottom hydrogen reaches at the top. The right one reaches here at the left. And left one reaches on the right. The front carbon in this Newman projection can be rotated by 180 degrees. Alternatively, we can convert this sawhorse projection into Newman projection by looking through this carbon-carbon bond as we have done earlier. Front carbon is drawn as green dot and back carbon as red circle. Front carbon has hydrogen pointing up. One on right pointing down and one on left also pointing down. The hydrogens on back carbon are exactly behind these front hydrogens, but are drawn slightly displaced for clarity as though the bond were rotated by a tiny fraction. If the front carbon is rotated by any other angle, for example, in clockwise direction, the sawhorse projection appears like this. This can be converted to Newman projection. The hydrogens on front carbon appear like this and hydrogens on back carbon remain unchanged. An infinite number of conformations are possible for ethane. Same as for any two atoms connected by a single bond and bonded to atoms, groups, or ligands. Any conformation can be specified by its dihedral angle. In case of ethane, it is the angle between the CH bonds on the front carbon atom and the CH bonds on the back carbon in the Newman projection. When the dihedral angle is 60 degrees, the conformation is called staggered conformation. That means the hydrogen atoms on the back carbon are staggered halfway between the hydrogens on the front carbons. When the dihedral angle is 0, the conformation is called eclipsed conformation. That means the hydrogens on the back carbon are hidden or eclipsed by those on the front carbon. This conformation where dihedral angle is anything other than 0 or 60 degrees are called skew conformation. In a sample of ethane gas at room temperature, the ethane molecule rotates millions of times per second, and their conformations are constantly changing. These conformations are not all equally favored. This can be studied by conformational analysis of ethane. Conformational analysis is the study of the energetics of different conformations. If we plot potential energy of various conformations versus the dihedral angle, the graph looks like this. With dihedral angle 0, the conformation looks like this, with hydrogens on front and back carbons eclipsing. Two eclipsed hydrogens are shown in red color so that we can monitor the rotation in the molecule. Rotate the front carbon by 60 degrees clockwise. We get this conformation, where hydrogens on front carbon are staggered halfway between the hydrogens on back carbon. In a similar way, if we keep on rotating the front carbon by an amount of 60 degrees clockwise, we will get these conformations. These are all eclipsed conformations. And these are staggered conformations. The energy difference between the conformations is 12 kilojoules per mole. That means, each CH bond on front carbon eclipsing a CH bond on back carbon contributes 4 kilojoules per mole. In other words, staggered conformation is more stable or lower in energy than the eclipsed conformation by 12 kilojoules per mole. This is the barrier to rotation from staggered to eclipsed. This resistance to the rotation or torsion is called torsional strain. and the energy required 12 kilojoules per mole or 3 kilocalories per mole to achieve eclipsed conformation is called torsional energy. At room temperature, this barrier is easily overcome and the molecule rotates constantly. The other possible conformations in between these two are the skew conformations and have energies in between these two extremes. Now the question is, why is the eclipsed conformation higher in energy than the staggered conformation? There are two reasons for this. The first is that the electrons in the bonds repel each other, and this repulsion is at maximum when the bonds are aligned in the eclipsed conformation. The second is that there may be some stabilizing interactions between the CH sigma bonding orbital on one carbon and the CH sigma star anti-bonding orbital on the other carbon, which is greatest when the two orbitals are exactly parallel. This only happens in the staggered conformation. Now let us discuss the conformations of propane. Propane is the next simplest hydrocarbon. Before considering what conformations are possible for propane, let us look at its geometry first. The CCC bond angle is not 109.5 degrees, the tetrahedral angle, as we expect, but it is 112.4 degrees. Consequently, the HCH bond angle on the central carbon is 106.1 degrees, smaller than the ideal angle of 109.5 degrees. This is not due to two methyls on central carbon clashing with each other, but instead, there is greater repulsion between two CC bonds than between two CH bonds. As in the case of ethane, two extreme conformations of propane are possible. Consider this one. When we look through this carbon-carbon bond, the methyl group on the front carbon is exactly staggered halfway between the two CH bonds on the back carbon. We can draw its Newman projection like this. This is the staggered conformation. If we rotate the back carbon by 60 degrees, we get this conformation. Here also, if we look through CC bond, the methyl on the front carbon is eclipsing with the CH on the back carbon. The Newman projection of the same can be drawn like this. This is the eclipsed conformation. In case of propane, the torsional energy of the eclipsed conformation has been found to be 14 kilojoules per mole. Since each CH eclipsing with other CH contributes 4 kilojoules per mole. Therefore, CC eclipsing CH must be contributing 6 kilojoules per mole. In the conformational analysis of propane, the graph of potential energy versus dihedral angle looks like this. When the dihedral angle between CC and CH is 0, we get eclipsed conformation. When the dihedral angle is 60 degrees, we get staggered conformation. Another 60 degrees rotation again gives eclipsed conformation. The torsional energy or barrier to rotation from staggered to eclipsed is 14 kilojoules per mole.
If you don't want to miss out important lectures, then subscribe and press bell icon for notifications of new lecture uploads.